Understanding how batch normalization solves critical problems in deep convolutional neural networks trained on medical imaging data. When training convolutional neural networks on grayscale MRI scans, we face unique challenges that batch normalization helps address. Let's understand the fundamental problem that batch normalization solves in deep neural networks. During training, the distribution of inputs to each layer constantly changes as the weights in previous layers are updated. In a deep network processing MRI data, each layer receives inputs whose statistical properties shift as earlier layers learn, making training unstable. The input distribution to layer n follows a normal distribution with mean and variance that change at each training step t. This constant shifting forces deeper layers to continuously readjust to new input distributions, severely slowing down training. Internal covariate shift directly causes the vanishing gradient problem in deep networks. As gradients flow backward through deeper layers, they exponentially diminish in magnitude, making early layers learn extremely slowly. The gradient with respect to early layer weights is the product of many derivatives, each potentially less than 1, causing exponential decay. In MRI scans, pixel intensities can vary dramatically across different patients and imaging protocols, amplifying this problem. This natural variation in medical imaging amplifies internal covariate shift, making the vanishing gradient problem even more severe. Batch normalization solves this by normalizing layer inputs at each training step. Batch normalization is inserted between the convolutional layer and activation function, normalizing the feature maps before activation. First, we compute the mean of the batch by averaging all activations in the current mini-batch. Then we compute the batch variance by measuring how much each activation deviates from the mean. We normalize each activation by subtracting the mean and dividing by the standard deviation, plus a small epsilon for numerical stability. Finally, we apply learnable scale gamma and shift beta parameters, allowing the network to undo normalization if needed. Batch normalization fundamentally improves how gradients flow during backpropagation. Without batch normalization, gradient magnitudes shrink dramatically in deeper layers. With batch normalization, gradients remain more uniform across all layers. By keeping activations normalized, batch normalization ensures they stay in the optimal range where gradients are neither too large nor too small. The gradient with respect to normalized inputs has a controlled scale determined by gamma and the batch statistics, preventing explosion or vanishing. The learnable scale parameter gamma provides a direct path for gradients, preventing them from vanishing in deeper layers. For MRI scans specifically, batch normalization provides crucial advantages. MRI scans from different patients or scanners have vastly different intensity ranges. Batch normalization standardizes these to a consistent scale. Different MRI scanners produce images with different intensity scales. Batch normalization makes the network robust to these variations. Patient-to-patient contrast variations no longer destabilize training, as each batch is normalized to consistent statistics. With stable gradient flow, we can use much higher learning rates, dramatically speeding up convergence without risking training divergence. Let's analyze mathematically how batch normalization improves gradient flow. The gradient with respect to the scale parameter gamma is the sum of gradients times normalized inputs, creating a direct gradient path. The gradient with respect to the shift parameter beta is simply the sum of output gradients, providing another direct path. Gamma and beta act as gradient highways, allowing information to flow backward efficiently, even through very deep networks. Forward paths flows left to right through normalized layers, while gradients flow back efficiently right to left without diminishing. Let's summarize how batch normalization solves gradient problems in CNN training on MRI data. Internal covariate shift, where layer input distributions constantly change, causes severe training instability in deep networks. This shifting distribution leads to vanishing gradients, as signals propagate backward through many layers. Batch normalization stabilizes input distributions at each layer by normalizing to zero mean and unit variance. By keeping activations normalized, gradients maintain healthy magnitudes throughout the network depth. The learnable scale and shift parameters provide direct gradient pathways, preventing vanishing gradients. For MRI processing specifically, this handles the natural intensity variations across different patients and scanning protocols. The result is stable, efficient training with consistent gradient flow, enabling successful training of very deep convolutional networks on medical imaging data.